I'm Antonio Sala, and in this video we are going to talk, without too much formulas or code, about what are physical systems, their mathematical models, and the computational models, simulation, digital twin stuff. We will be based on a, let's say, water level case study. So, for instance, the picture on the left is the actual physical system. You can have a tank with some reagent whose level you wish to control, or you are storing cold water for something else. So you have something that has an outflow. It's not totally obstructed down there, so there is water leaking, and having an inflow. And of course the flow balance would make the level rise or go down depending on whether outflow is smaller or larger than the inflow. So well, this is the physical thing, and we wish to understand it. How can we actually understand that stuff? Well, we can understand it by just common sense, intuition. Water tanks have been around for 3,000 years since irrigation appeared, or even, storing water for drinking. So we do understand what happens in this kind of systems. Indeed, if I don't put any water in that canteen, and if I put a lot of water, it starts filling up. And if I put an intermediate amount of water, then it's emptying again until, well, inflow and outflow do balance, and the tank stops getting empty. So, well, this kind of behavior is intuitively understood by most of us. So that common sense explains, this evolution of level in time as I change the inlet flow at will. So, common sense is the thing to understand first, because there is no need to know advanced mathematics to empty your sink once you have finished cooking. Okay, so what's next? Well, the thing is that 3 centuries ago, roughly, people invented mathematical models of dynamic systems, and people invented differential equations. So the physics by then argumented that you could study this kitchen sink by studying the mathematical properties of this differential equation that you see on screen. So this was a motivation for mathematicians to pursue the study of these differential equations, because that was the language of nature. Good. Then, with some math, you could estimate some properties of the kitchen sink so that you can roughly tell how long it takes to empty or to fill or whatever, or which level will it fill up to. Good. So then, the last third of the 20th century came, and computers were developed so that we could approximate the differential equations by so-called numerical simulations, computational models, so that we may build a sort of copy of my kitchen sink in a computer. What is that copy? Well, that copy is some code whose details, of course, are not the goal of this introductory video, no formulas. But okay, this thing I highlighted in blue is the Euler integration approximation of the differential equation, so that this constitutes the computational model of my tank. So running that computational model, I can play and see what happens when I open and close the valve of the inflow, so that I empty I fill the tank at will. This software is called a simulation model, a computational model, or digital twin, depending on the marketing leaflet you're reading. But it's sort of the same stuff. It's a software copy so that I can predict what will happen if I do certain things to my tank. And what's the use of that thing? Well, okay, if the things I predict that will happen are not satisfactory to me, if I am in the design phase, I still not build this physical system. I am deciding its size, the size of the pipes, the size of the inlet pipes. Well, okay, I can simulate them, see what happens, and only when I am satisfied with the rising and lowering of the level here and my movements of my inflow, whatever, when I'm satisfied with this, I will finish the design phase, and then I can build a prototype that hopefully works as expected. So computational models save a lot of money because we can avoid wasting time and resources building prototypes that will not work as intended. So computational models and simulation are nowadays of key importance in the design phases before building things. But they are also of use even after you have built the real thing. You can use these digital twins, these digital copies of the physical system, for a handful of things. The first thing is that, if you feed them with the same input, then if the model is correct, the levels, pressures, and whatever variables of interest in my computational simulation will be the same or roughly close to the ones in the actual physical system. So I can use my model running in real time in parallel to my actual kitchen sink in order to estimate the values of some internal variables I might not have an actual sensor with electronics and instrumentation in it. So maybe I do not have a pressure sensor at the bottom, but okay, I can do some computations with formulae about which pressure I am having at a particular moment. So the idea is feeding my model with the same inputs as the real thing. And there is a more advanced methodology, which is called observer, in which I feed not only the inputs, but whatever physical sensors of levels, pressures, flows, or whatever I have in my system. Then everything is mixed together, and I can build so-called smart sensors that can mix simulation and actual readings in order to better estimate internal variables for which I do not have a sensor. So that kind of software that is fed with system inputs and system sensors and computes via, of course, simulation models what's happening to internal variables I do not have a sensor for. That's called an observer, and there is a whole theory on how to build them in order to be the most accurate possible. But of course, we are in an introductory stuff, and we are just posing the things that we can do with those models. Good, so we can estimate variables. We do not have a sensor with these models and the observer software. Another thing we can do is, say, if we realize that my system is not acting as my simulation, for instance, I can simulate a batch of models with different outflow pipe characteristics in order to see which one fits best my historical readings. This is called physical parameter identification, experimental identification, and for instance, I can detect that the outflow is lower than expected and use that identification, for instance, for fault diagnosis in order to detect an obstruction of the outlet pipe. How? Well, simulating different outlet pipes and superimposing them to the actual experimental measurement of level. So, in summary, we can use models before the system is actually built to avoid creating useless prototypes, and we can use computational models and mathematical models, of course, because they are at the core of these simulations. We can use them even when the system is already built as digital twins in order to observe unmeasured variables or to identify changes in physical parameters of my system, identify failures in my pipes or sensors or whatever. There is a last use of models which is of paramount interest in automation science. Which is it? Well, in many cases, my goal of building this and adding some software is to tell the software that I want a particular water level so that it automatically, without human intervention, opens and closes this valve so that the level is achieved. I mean, in this case, what the user inputs is a desired level, and then automatically, if the user wants a lower level, then something closes, and then when the level reaches below the desired one, then it opens the valve. So at the end, it's the level set point reference, the user input, and the one who decides the inlet flow is software called control software. So this is a simulation of a controller that, of course, in most cases is based on the error, the difference between the set point, the desired value for the level, and the actual measured level. It's a feedback controller in this case, and does some operations in it. So this kind of codes are called controllers. Then simulation models can be used to test that control software so that we can check whether the level that the user wishes, this red set point, is reached in a particular time or in a particular way. So we can test that control software quickly without actual use of resources, reagents, water, whatever, just in my computer, and when that works correctly, then I can actually implement the feedback control in the real thing. So I buy a motor to open and close this valve, that's called an actuator. I buy some level sensors and I program in a so-called programmable logic controller or industrial controller or a PC. I do program this control software. So this is the last use of models, okay? The models can be used to design the actual system, the pipe diameters, the tank section, whatever things, and can be used to test control software. And when everything works as intended, then the actual physical system and its instrumentation is actually built. And we'll finish it now by just summarizing in half a minute what we have said in this video. We have discussed with no formula what is a physical industrial system, what's a mathematical model of it, and what's a computational simulation digital twin model that is implemented in software. These models have a lot of uses in industrial applications, from pure simulation so that the operator acquires some common sense knowledge before breaking things. Pilots first drive a flight simulation before actually crashing an Airbus plane. We can use the models to design the process and see if we need different pipes. We can use the models to design control software in a faster way than doing lots of tests and experiments on the real thing. And we can use the models in real time, the digital twin, running in parallel to my system as observers, smart sensors, estimating what's happening inside, even if I do not have a physical sensor for that particular thing I am interested upon. Or we can use it to identify physical parameters and diagnose faults. So these are all the uses of mathematical and computational models of my systems, so that it's of paramount importance in industrial engineering. And this is why industrial engineering courses have simulation courses, system dynamics courses, control courses, and physics and differential equation courses, which are the basic science in which all this is based. The details of all that is, of course, a whole degree in engineering science, lots of textbooks, and of course, my collection of videos develops particular aspects of these issues, so you are invited to watch them. For the moment being, this is just an introductory video, so we'll stop here. Thanks for watching.